Hey, I think we're ready to get started now. Good God, where did the time go? I mean, I did leave the office a little bit later than usual today, but, I was, getting home, preparing for a shower. It was 6:30, and then all of a sudden, I got out, and it was 8. That's crazy. Don't know how that happened. It usually does not manifest in that way. Oh, good God. Okay. Whoop. Transition on over. And let's see, make OBS look normal again. There we go. Okay. I think everything is working again with no hiccups. No more hiccups regarding audio. Glad it was just the intro that had that. So hi, welcome everyone. I'm your streamer, Crash Icarus. I do like games and stuff, and apparently the and stuff also involves chemistry. If the iconography on my chest was not an indicator enough. Today, well, currently you're looking at a wonderful cover of Mega Man 9's soundtrack by SN Fox. I just happened to find this while browsing earlier in the week. I think that the Wily Wars sound chip is, sound chip I say, but the Wily Wars sound font is very, very well suited to Mega Man 9's orchestration, or composition, that's the word I was going for. I'll be putting this on in parts as we go over the video today. But, yeah, I hope everyone's doing okay, and, ready to learn some hot chemistry information. I have a limited amount of, okay, I did not prepare really at all, actually, to explain the concepts, but I am familiar enough with what's going on. But we'll just let the Australian science man talk first, and we'll see, what gaps I need to fill in. I encourage you to ask questions if things don't make sense. But I also just encourage you to have fun with the Australian crackshed shit posting, because that's honestly where I get a lot of my enjoyment from these videos as well. So, with that, I will pause the music and move on over. The bastard changed the title a couple times during the week. Now my thumbnail is slightly inaccurate. Grr, oh no. How will I ever recover?
G'day, welcome back to another episode of Extractions Ire, and once again we're continuing on our material science journey to make something that glows cool. That's the point of the chemistry this month. If we make something that glows cool, we're successful. And
I love the shitty
if we
word
screw
art.
it up, which happens sometimes, it won't glow. I've done a few
sometimes
videos looking at fluorescence recently, and once again, we're going to be looking at fluorescence, but this time we're looking at upconversion fluorescence. So in this upconversion fluorescence, we're going to shine in low-energy infrared photons and emit higher-energy visible photons in the red and green, which does feel like it will violate the conservation of energy, because the photons we're emitting are at higher energy than the photons we use to excite. But it is possible. First of all, let's talk about the material we have to make. So we're focusing on rare earths. So we're making a erbium and ytterbium doped yttrium oxide. So we have yttrium, erbium, and ytterbium. Yttrium isn't in the lanthanide section, but it's classed as a rare.
Typo spotted. Yttrium oxide. That doesn't make any sense. I'm sure he's probably, he might mention it, but fun fact is that all three of those elements are actually, pretty sure erbium is anyways. I'm pretty sure all three of those elements are named after the exact same mine in Sweden, the Ytterby mine, because they were all just found there, and it makes the periodic table, of course, not more confusing at all whatsoever. It's definitely still completely intelligible and not at all difficult for undergrads to understand.
Rare earth because it chemically is very similar to all the other lanthanides, which are rare earths. And also scandium is also a rare earth, but no one really cares about scandium. Because erbium and ytterbium have similar chemical properties and ionic size as yttrium, we can make this yttrium oxide where some of the yttrium ions are replaced by erbium and ytterbium ions. So what's special about this material? Well, lanthanides have electrons in their f orbitals.
Alright, I think we're maybe getting a little past some heady concept, but I guess, okay, to recap in maybe a slightly more interpretable fashion, let's see. So doping is, in the material science world, a term used to describe what happens when you want to replace some atoms within a material with atoms of a different element, but not enough of them to really constitute a different formula or a different change to the structure, but just enough to kind of give it a little bit of, variation, introduce some chaos into the structure. So, for example, let's say a simple crystal structure would be something like, good old sodium chloride, table salt. I'm sure any of you watching Jimmy Neutron are familiar with this little one. And sodium chloride has this square lattice shape that just kind of goes on into, well, not infinity, but up until the crystal is done having, it reaches the boundary. There we go, that bond goes back there. And, this repeats on, roughly infinity. And say, you had a very large cluster of these, stacked up against each other, and you just had it continuing like this, and sodium chloride going up and there, and doing all this, and, it continues going on like that in all directions. If you, for example, would to dope this with, say, potassium, that would be the equivalent of, say, replacing the sodium with about, I don't know, just a very small amount of potassium ions. Say, like, I don't know, 0.01 times potassium ions. For every 100 sodium atoms, there's 1 potassium ion. There are benefits to this, which I'm, not sure how far he's going to get into in the video. If I maybe sweep the timeline a little bit. Looks like he's going to get into maybe the explanation of upconversion in a little bit, so I won't go too far into it. But what this is good for is introducing defects into the structure which have a requisite effect on the orbitals within the structure. An orbital is it's the rough volume that an electron can occupy based on how much energy it has, and they are often represented in diagrams by just having, they're often represented in energy diagrams just by having horizontal lines on versus a y-axis of energy. I probably shouldn't have drawn those dashed lines there. Oops. And by introducing a couple of different atoms in a large solid-state structure like this, you can, I keep saying it's just a verbal tick. You can kind of move the energy levels of the orbitals a little bit around, and that'll allow you to absorb absorb light at different frequencies, because light is what will move an electron, represented by one of these half arrows, up to another orbital. And when that releases, it will also release light, and with the fancy engineering that he's going to try to explain here, the material can be coaxed to absorb low energy light, combine a couple of photons of said low energy light, and give off a high energy particle. The utility of this is mostly for solar power, photovoltaics, basically just to kind of help get some more energy out of the low energy light that the sun emits, not just the UV light, but there are also different applications for it as well. Hopefully that's a good primer for what we're about to talk about. It's definitely not a full explanation of the picture because, again, that would require like a whole graduate level class. But, I do have some, I won't say not necessarily fond memories, but, I do remember learning about this in my graduate level classes. Not this particular material either, but I did have to prepare a PowerPoint once for a assignment where we got to just pick a different topic in photochemistry and talk about it for a while. And I had to learn what upconversion was, and it's actually well, for me at least, it's pretty fascinating stuff. Just because it's the ability of, well, let's just, let's kind of work against the natural way physics wants to work, and kind of engineer something to make solar power more efficient. All right. Go back to
Electrons
this.
have geometry. This is something you kind of learn.
Oh yeah, and this is what he was saying with the orbitals, and these are These are the F orbitals, which, oh, well, I guess I'm going back to the explainer, huh? Oops, I forgot to write on a different layer. There we go. So you have different shapes of orbitals. Again, orbitals being the rough volume that an electron will occupy based on how much energy it has. And there are multiple different types of orbitals, and they just kind of fill up sequentially as you go along the periodic table. So if you have an element like, let's take helium. Helium is very simple. It's the second element on the periodic table. It has only one orbital that's full with 2 electrons. It's the second element. It needs 2 electrons to balance out the 2 protons that it has in terms of charge. And so this would be the 1s orbital. If you go up higher to then lithium above it, the third element on the table, it has 3 electrons, which one would be this 1s, and then at a higher energy above it would be the 2s orbital. These are all shaped like circles, or well, they're shaped like spheres. I can't really draw a sphere very well, but you know, take it as a circle as you will on the piece of paper. This would be a bigger sphere because it's of a higher energy. If you go further down the table, and let me just look at my periodic table, and let's say I don't want to draw a whole lot of things, but you know, as you get further down into the table, you will find then there's p orbitals, which are shaped like dumbbells. Then you get to d orbitals and the transition metals in the middle, and then you get to f orbitals in those 2 blocks below the periodic table, the lanthanides and the actinides. And orbitals dictate bonding. It's how electrons try to communicate with each other across atoms. Shapes are different. Energy levels are different. It kind of brings about all of the photochemistry we're about to talk about. Oh, and wow, Splash Woman's music kindly fades out as we resume the video.
Electrons in their f orbitals. Electrons have geometry. This is something you kind of learn in university. All these electron shells have geometry. Some of them are very simple geometry, and you get a bit more complicated as you go further down. But the f orbitals have very strange geometry, let's just say that. Because of their strange geometry, a lot of the electron density is sort of inside the other electron shells, which are, you know, spheres or whatever. Once again, it's sort of probability fields. And the point is, a lot of these shells
F electrons are so the geometry is so awkward. They basically never do bonding, but
shells are actually shielded by the other electrons, so they don't really see the environment too well. You can excite the electrons between these.
Sorry, where's that picture? I feel that on a spiritual level. I have a very negative memory of trying to figure out in university why on earth do in the metal series, because the electrons fill up orbitals by what is the next lowest energy they can, by what the next lowest energy configuration is. So that's why 1s gets filled up first, then it goes to 2s because that's the next lowest, and then 2p, and then 3s, and so forth. And it took me the longest time in university to figure out, like, okay, well, why is 3D get filled up after 4S? Normally, the number is, like, the more important part of, like, filling things up. That's, like, the tier of energy that you're really looking at. And I had to think about, like, quantum confinement and particle in a box, and, like, how the more complicated the orbital gets, there's, like, it might be smaller than what's above it, but it's higher in energy because of how much bending is involved with it. It's fucked. And yeah, imagine a helpful picture here is so hard. It's so true. It goes so hard to, like, the experience of trying to learn how to talk about these damn things and think about them.
So they don't really see the environment too well. You can excite the electrons between these f orbitals, and they can't really release that energy into the other shells or into the environment very easily. So you have these excited states which last for a very long time, which for atomic timescales is on the millisecond timescale, which is way longer, way longer, billions of times longer than usually an excited state would live for. So how are we achieving upconversion? All right, so
Okay, so when he was saying excited state, that would be referring to what I was kind of diagramming earlier, where if you have an electron here and you got some light coming on in, and let's just draw like a happy little Mr. Sun over here. You got light coming on in, and it tries to bump one of these electrons up to, go up here. Actually, I should just draw that. Wait, how do I draw that? Good. There we go, that's better. Bumps up an electron up there, and you can have sometimes these electrons will stay in... That's what's called exciting an electron from the ground state. It's excited, it's absorbed energy because of light, which chemists will often abbreviate as H nu, because that's the mathematical equation for the energy of light. What was I saying? And then, yeah, sometimes, whenever the electron goes back down, it re-emits that light, but you get fluorescence when this electron picture becomes way more complicated, and say like it tries to go up to a third energy level, but then because the third energy level is close in geometry to the second energy level, you lose some of that light energy to heat instead of actually emitting light back out. But then that second energy level doesn't want to go back to the lowest energy level because the geometries are so different there that it can't do it very easily because of quantum mechanics. And so you end up being stuck with a photon that really doesn't want to go anywhere, and so you get this long-lived kind of light state until long-lived emission of light until the electron finally says, "Fine, I'll go down. I don't want to, but I will." And that's yeah. So now we're going to talk about how you actually harvest this kind of stuff. How do you actually turn that into multiple photons of low energy, turning into one of high energy?
Have an erbium ion here, and under normal fluorescence, we would put in a UV photon, it would excite it to a higher state.
Also, yeah, that's why I didn't try drawing the a more accurate orbital diagram. It gets complicated really fast.
And under normal fluorescence, we would put in a UV photon, it would excite it to a higher state, and then decay and release another photon, which, has lost some energy in that ion. But because this rare earth has so many levels and the excited states are so long-lived, we can actually send one photon in, excite it, and then re-excite the ion with another photon. So now we've put in two photons, kind of pooled their energy together so that when we emit a photon, it's actually at a higher energy than the two that we put in. So we just have half the number of photons at twice the energy, assuming 100% conversion, which is certainly never the case. Ytterbium and erbium ions together is a very common pairing of rare earth ions because the ytterbium itself is very good at absorbing light. So it absorbs light at 980 nanometers, and then it can pass on that energy to the erbium. So you have this sort of absorption, and sometimes it's called a sensitizer, and then an emitter ion. Ytterbium-erbium is a common pairing, but there's also ytterbium-thulium. Thulium can absorb 5 photons and release 5 times the wavelength. So you absorb in the infrared and emit UV photons. Praseodymium is very good at it. Holmium can do it. These upconversion materials are often found as...
Also, I guess something good to add for context of why is ytterbium, or why is ytterbium, or is it yttrium? Why is yttrium so good at absorbing this specific wavelength and the other ones are so good at emitting? Well, it has to do with just what the orbital structures come out to, and there's not really a better answer than that. It's just kind of... It's at a point where you're asking a question of... The question you have may sound simple and innocent, but the real question you're asking becomes, why is quantum physics the way that it is? And you just kind of have to sit back and say, look, protons, neutrons, and the nucleus just kind of said, this is what I'm good at, and this is the element I've become. You just gotta roll with it at a certain point. Questioning the universe tends not to go very well for scientists.
upconversion nanoparticles, and they have very cool applications and kind of have been very popular in the 2010s. There's been a lot of publications written about them, and I can be a bit cynical about that because I've also done like 3 or 4 upconversion papers. It's fine. Everyone's got an upconversion paper. They've got cool applications mainly in biosensing because the human body is not particularly transparent to UV or visible wavelengths, so it's very hard to study fluorophores through skin. But there is some sort of transparency in the infrared. There's some sort of biological windows, they're called, and if you can excite through them with your high intensity source, you can kind of excite the visible light and then image that visible light. Also, there's big applications in solar harvest.
Yeah, that's the one that I'm thinking of. I've never actually heard of its application in bioimaging studies, because that's interesting. What they would want that for in bioimaging is if they're trying to insert new proteins or examine, like, say, track like a piece of RNA that they put into the rat, or a new kind of drug they're trying to track. They would have like some kind of emitting group on the chemical they're administering, and to kind of measure like where it's ended up. If it's like, say, targeted the cancer cells or something they're looking at, they would then try to shoot light at it and try to make it re-emit to understand where it ended up when they're doing the autopsy of the mouse. But yeah, I guess that is actually a really interesting point, to make it try to emit in that infrared field. I never thought that this would actually and then actually recapture that into a more visible manner that's easier for us to interpret. I've never thought of doing it that way. Huh.
Trying to get extra energy from the sun, because silicon solar cells can only absorb up to about 1,000 nanometers. So if you had a material that could absorb, say, over 1 micron and then re-emit that light at a higher energy, then you wouldn't lose that. You'd be able to sort of upconvert and then reabsorb it. It is, of course, very difficult to have an upconversion material that absorbs the infrared without blocking the visible light getting to the solar cell. There's a lot of organic upconversion schemes which are sort of have an organic sensitizer and an emitter, and they sort of work together in a different way that it works with rare earths, but today we're just focusing on rare earths, which are much simpler and just have long...
Yeah, fuck organic chemistry. Homies hate organic
enough
chemistry.
About applications. We're here to make something glow cool. So how do we do it? Today, we're going to do it through solution combustion synthesis. Now, you can tell I'm smiling. I'm very excited about solution combustion synthesis. There's a lot of ways to make upconversion nanoparticles. A lot of the time, you make a hot solution and you inject in these things and they have rapid growth of small particles. But I've always wanted to do solution combustion.
I've never heard of this kind of thing, but sure, Tom.
Oxidizers out of your rare earth materials, mix them with a fuel, make it catch on fire, and everything burns really quickly and makes these oxide particles, and somehow that works. So I have some of the rare earth metals, and we're going to make nitrate salts out of them, mix it with a fuel.
Fundamentally, it makes sense. So I guess background for him. Tom is he technically has a degree in physics, but he's done a lot of chemistry because of the nature of his research. He tends to lean a lot more towards the analytical side of things and less in the synthetic side of things, which is very funny considering he runs a synthesis channel very, very much so. Meanwhile, I am the opposite. I was much more of a synthesis person when I was in university and grad school, and not very much into the analysis stuff. So listening to Tom talk about doing chemistry sometimes can be it can be like, okay, I mean, you're kind of getting the gist of it. It's like, yeah, if you oxidize your things and then react with the fuel, like, you're oxidizing, like, yeah, you're making like oxides. That's how you make oxides, Tom. That's what combustion is. You know this. You're a PhD. Like, come on. Maybe he'll completely obliterate a gummy bear by oxidizing it like my chem teacher did. Oh yeah, that's a classic experiment. I love watching that happen. Putting it in, especially when they do it with what is that? Liquid potassium perchlorate, which, man, to melt a salt is really something that you have to commit to doing. That is an angry liquid that you make when you melt that, and very much demonstrated by the fact that, yeah, you throw some sugar in there, it lights up in big purple fire. It's not happy. I'm getting the feeling he's, based on some of his other alternate thumbnail options he had for this video, Tom excels in making organic tar out of inorganic materials. He somehow does alchemy and is like, okay, I didn't know it was possible to, like, to get sticky garbage out of salts, but he does it sometimes. And I'm jazzed to see how he manages to absolutely just munt the synthesis. It's gonna be great.
Set it alight, and then we're following this paper. They say it needs an anneal step at 800 degrees. Not entirely sure how we're going to achieve that. We need to do an anneal step as well, which will...
Yeah, I'm not sure how you're going to do that either, Tom, when you've refused to have anything other than hardware store parts, but that's what makes the magic in this video. Think about, given your love of chemistry, have you ever passing interest in Godzilla kaiju stuff? It'd be up my alley. A little bit. I mean, I've watched, like, you know, a couple of my fair share of, like, kaiju movies and stuff like that. It's fun. It's not my main dig, though. There's, like, it's same thing with kind of, like, maybe Jurassic Park. It's cool to see the science application, but, you know, usually the main... They use science, and then they just steer it real quick over towards action. I kind of prefer when it's, like, you know, the science is more front and center, and I would watch something like, say, a Star Trek, which has a little less front and center than maybe my example, maybe than I would like, but it's closer to that, you know. Kaiju stuff's still fun though.
Improve their crystal structure. So we're going to make the nitrate salts, set it on fire, and then really heat it. To see the upconversion fluorescence, we need an infrared source, and I have bought a 980 nanometer laser. It's 500 milliwatts. I'm a little bit scared of it because I haven't fired any lasers here in the lab before. I don't have the laser safety glasses for it, so I can't turn it on yet. There's a bit of safety stuff I've got to fucking work out, but that's the intro. Let's get to the chemistry. Oh, actually, but you allow me 1 second of self-promotion.
Your first exposure to oxidation came from Destroya's oxidizer beam, which is a very distinct purple color. Ooh, that's nice. I'm trying to think. What's a typical purple oxidizing type thing? I mean, it's probably not permanganate. That would be crazy. But I think there's a handful of the noble gases that are purple when they're, well, I guess technically oxidized, more like have a current run through them. So yeah, that's kind of a good representation of that. Could also sort of be ozone. Ozone kind of can take on a purple-y-ish color sometimes when it's you know, at high temperature, high energy. So it's yeah, there's some science related to that. I like that. Of course, your more everyday exposure to oxidation will be rust. That's why, you know, cars rust in the middle of winter when there's all this salt and other shit applied to it. It's iron turning to iron oxide.
I've had a Patreon for many years, and it's been tied to Explosions&Fire, and
the
charged
shielding
people when Explosions&Fire uploaded a video, which wasn't all that often. Patreon as a whole has moved to just purely monthly subscriptions, so now the energy of that Patreon is trying to support this channel, Extractions Ire, and my quest for monthly uploads as well. So if you ever want to join the Patreon, you can join for free and find out what I'm working on and what's coming up next and etc. So anyway, bloody hell, let's get to some chemistry. I have some rare earth metals. They are somewhere. Why is every first step of these videos just trying to find shit in this lab? Where are my rare earth metals?
Gee, Tom, I wonder if you could maybe organize your lab a little better. You wouldn't have this problem.
Of rare earth elements. I got these, I want to say 5 years ago. I don't know, when was COVID? How long ago was COVID? Probably got these 7
Don't ask,
years
Tom.
ago. God damn. Time goes
Don't
fast.
ask.
Maybe 8 years ago. This is not all the rare earths, but a selection of them. I wanted to make a video about making cool colored fire or something like that. So I got all these, and they've held up pretty well. The neodymium is the one that's really been oxidized quite a lot. I don't know if that's because neodymium is more reactive. It might be. Also because maybe it's in this different container. It's reacted a bit more than all of these. But
yeah, Tom, I'd say it's probably because it's in the vial that isn't airtight. That maybe makes sense.
They've held up really well. I'll get some close-in shots, but I sanded a couple of them back maybe 3 or 4 years ago in order to try and film this video, but didn't end up really doing much with it. But you can see where I've sanded it back, and they haven't really oxidized that much. So while they do oxidize, they are mostly air stable. So we've got holmium, yttrium, samarium, ytterbium, gadolinium, not all of them, but a cool selection of them, and we'll be using erbium, yttrium, and ytterbium today. There's only a couple grams of each of them. I got these off a guy called Pete several years.
It's just such a shame that almost all the metals on the periodic table are just, you know, silvery lumps. They aren't, you know, interesting colors. You really only have copper and gold for interesting colors. It's a shame.
Years ago, thanks Pete. I wonder how Pete's doing. I remember his Skype profile picture was of a sausage dog. The dog's name was Otto. I don't know why I remember the dog's name. Nice guy. We'll use all of the yttrium because we need quite a bit of yttrium. And we'll probably use half of the erbium and ytterbium. We might as well dissolve them up separately, and then we can weigh out specific amounts of the nitrate once we've made the nitrate. So I'm just going to put them in a little bit of water. They might react slowly with the water. It'll be interesting to see because you generally don't see these metals reacted very much. They're a little bit obscure, if not particularly
actually
rare.
Water
these
reacted?
are our three. Visually,
I think they
you
were.
can't really tell these apart. Samarium tends to be a bit more dendritic, but I think that's maybe just the way that the metal is formed. Ytterbium is maybe more gold, but that's just the oxide sort of sheen, and they're all really kind of silvery metals. Neodymium kind of has that purple coloured oxide layer. You can see that there. Erbium oxide layer hasn't really formed that, but it's much more pink. So generally when they have a big oxide layer, you can tell
Can't really see
apart
that,
a
Tom.
little
It
bit,
doesn't
but
show up on the
when
video.
they're in a nice form of metal like this, and these are quite pure metal chunks. Thanks Pete once again. They'll just look like little lumps of metal. They're quite dense. You couldn't tell that was holmium without some real serious tests to determine that it was holmium.
So let's see. You thought cobalt was a distinct blue color, or is cobalt a compound and not an element? You forget. So cobalt is an element. So you are right on that one. Good job. I don't know why I didn't mean to sound condescending there. Good job, genuinely. You're thinking of cobalt blue. So cobalt blue is a a historical pigment that is a cobalt aluminum oxide combination. And again, due to how all of this orbital shit interacts over on the right, and how it absorbs light and moves it around and moves it between atoms and between orbitals and all this stuff in different geometries, it ends up being very absorptive of, what's the complement of blue? Orange light. It ends up being very absorptive of orange light, and so it ends up looking blue because it ends up reflecting more blue light than its complementary color orange. This has been like a long known historical blue pigment, so it kind of has that reputation, kind of precedes the reputation for the metal cobalt. Otherwise, cobalt itself is it's pretty let's see here. Cobalt, it's just gotta just be a link to cobalt on this page. Don't make me actually look it up. I guess not. Okay. Otherwise, cobalt is just another silvery metal. Many of them on the periodic table. It is fascinating how just doing some extra chemistry and unlocking like some oxides and some other groups to put on the metals can really change their color quite a bit because of just how you free up the electron structure. And it's a whole, again, that's a whole lesson on its own, but it is really kind of cool to think about. Yeah, thank you. I'm not condescending. I'm trying not to be condescending. It just kind of comes with my tone. I try not to be, but I tend to realize that I just kind of say shit, and I'm like, oh, yeah, it's sort of correct. And it's like I have that snobbery about me. I kind of check myself as much as I can. Yeah, metals have the dullest colors. If you want fancy stuff, you got to look towards geodes. It is pretty cool. I mean, I do have. I need to actually show off my metal collection or my mineral collection, but like you can get some really. I mean, metals are kind of the key to a lot of interesting colors, and it's because I might as well actually rant about this a little bit, or not rant about it, talk about it a little bit. So, the reason that metals tend to make for very interesting colors is, it kind of relates to just like, this is quantum physics and this is the structure of metals because the universe said so. but say if you take a orbital structure of cobalt, I guess I'll also mention that like these are the, let's see, these are two different 3D orbital sets within a not octagonal, octahedral coordination environment. So that was a lot of words. So let me say this. We usually call this the EG set and the T2G set. These are all a bunch of abbreviations to kind of basically say that the orbitals are shaped one way and they have this sort of symmetry to them. And to be in an octahedral set, so we would have OH, that's how we would designate something as octahedral. And we could say take a metal and then make some dashed lines. This one's going out of the page. Ligand. Okay, so the L just stands for ligand, which means thing that is bonding into the metal. You end up getting orbitals that kind of have this spread of electron geometry. And this is just for generic metal. I'm putting some electrons in just to kind of give a picture of what's going on. When you go from just a generic metal, so like a metal that is just kind of free-formed in space, and you just have one metal atom existing, and you would say have, let's keep the number of electrons the same here. That would be 4 plus 3, so 7. 2 of them are paired. 2. This would just be a big combination of 3D, let's say, orbitals, if we're looking at that first row of transition metals. And this is just a metal atom out in space. Once you actually coordinate ligands to it, what happens is that since the symmetry is no longer spherical, the d orbitals are all different shapes, and so I guess I could pull that up, take a look at that. Orbital. Atomic orbitals. Not a good one on Wikipedia, huh? Alright, d orbital. Hey Chris, thanks for stopping in and saying hi. Maybe you'll enjoy the science lesson, maybe it's a gigantic headache. Maybe both. Pearlescent colors. We'll come back to that. But yeah, so the d orbitals have this kind of shape, and you can see that they are kind of in different orientations around different axes, and conveniently, the way I've drawn the diagram is also kind of how it ends up being shaped, it corresponds to the 2 on top, 3 on bottom structure that are on the actual screen right now. So you would have these two shapes on top. They get the best bonding interaction. As you can see, they kind of are directly lined up with coordinate axes, and so the ligands bond into them good, and that causes the orbital energy to rise. These are technically anti-bonding orbitals. It's because they bond into it, and then these are the ones that go high up. Again, confusing. Try not to get too heady about it. But anyways, to return to the point, when this happens, when you have ligands bond in and break this spherical symmetry here on the right, it now actually becomes that this energy difference between the two orbital sets, that energy difference almost always corresponds to, I'm not gonna say almost always, with like most ligands you could throw at the metal, that almost always corresponds to the energy of visible light, or of, you know, some wavelength of visible light. So for some metals, it's good for absorbing red light. For some, it's good for absorbing blue light, and, you know, etc. And if you absorb red light, then you get a green compound. If you absorb blue light, then you get a orange compound, and so on and so forth with complementary colors. And that's just how the metals of the table work. And so metals are responsible for a ton of different pigments because of this. It's crazy how that works. It was kind of like so cool to me when I was, you know, learning chemistry for the first time. I was like, wow, really? Most of the pigments are metal-based? I never thought of it that way. And then it's like, oh, it's this weird coincidental energy thing that's even more amazing, that just kind of by the coincidence of the universe that metals kind of manifest colors like that. Now, they're not the only things that manifest colors. Organic compounds, those made of predominantly of carbon, hydrogen, and a couple other things like oxygen, nitrogen, etc. Those also result in colored compounds. Well, that has less to do with things bonding into given atoms and more having long chains of double bonded atoms together, because it kind of forms like a big cloud of p orbitals that are connected. If I were to say draw a new thing like that, say I had something like I don't know what this is called necessarily. Well, actually, I could just pull up a diagram, an example from Google. So let's see. Organic dye compounds. Let's get one that was scanned in maybe within the current decade. Yeah, okay, that works. So I copied this, moved it over here just so I could draw on it a little bit. Expand canvas, sure. Okay, so you can see how... Let's see. For something like... Oh, what's kind of simple to explain? None of these are really that simple to explain, but let's just say looking at quinazerine green. That's a fun one to say. You can see that there's all of these multiply bonded carbons kind of in a row like this, and then that kind of also further extends into nitrogen. It has two lone pair electrons. Those can kind of donate, and they're in the same geometry as these double bonds, because these double bonds represent p orbitals above and below each carbon. You have electron density being contributed from all the carbons, from the nitrogen, and you can see there's kind of just this big chain of dumbbell things up above and below each of the carbons and these atoms. And so because you get just this big cloud of electrons, you end up lowering the gap between the orbitals again of these bonds, so that way you actually have, once again, visible light can be absorbed there. So that's where a lot of the organic stuff comes. I don't know what pearlescent colors are Grim. I never really took classes to kind of hammer into pearlescence, but I'm sure it has something to do with this. Punt kick the conjugated pi system. True. Put that shit right into the sun. Hello, Ryan. Nice to see you. We're taking a detour from the actual video we're supposed to be reacting from, because I explain chemistry to my largely non-chemistry audience, because I'm a big chemistry nerd. You fell down the metallic rabbit alloy hole, and apparently we actually have real-life ceratanium. Oh, like from Mega Man. So that means one could theoretically recreate Mega Man's armor using the actual material it's of. Actually, so ceratanium. Ah, huh. Interesting. High strength alloy. 14-inch alloy. Huh. I'll have to take a look at that. I'll be interested in what the properties are later. Because alloys are some pretty cool stuff. You can have some really, interesting things. Like, people have made metallic glasses out of very complex alloys, and that just basically means that the metal atoms are in a completely chaotic structure. There's no order to their arrangement, and metallic glasses have a very fun property of being extremely elastic. So if you were to drop a ball bearing on it, it would bounce up and down on it like a trampoline and lose very little energy with each bounce. It's really cool. Apparently they make watches out of ceratanium. All right, I think that's enough side tangent yapping. Let's get back to the shitposting chemistry video. Pausing the Mega Man 9 Wily Wars audio. Go check out the full thing. It's not me, but I won't feel like shouting out the person who actually made it. I might as well check in. How's my mouth sync looking? Looking bad. Okay, let's fix that. Okay, there we go. All right. Anti-shoplifting tags got metallic glass in them. Oh. Oh, that's interesting. I wonder why that is. Is it like it's just to have something dense, but then why would it have to be metallic glass? Does it have to reflect something in a certain way? Does it just have to be durable? You know the answer, Ryan. I'd be curious to hear why.
So I've got basically all the yttrium and all the erbium I have, but about half the ytterbium, just because the ytterbium is into nice blocks and I don't really feel like breaking up these big blocks of metal, so we might as well just dissolve them all up. We'll add just a little bit of water, see how they react, because we don't want it to go too crazy when I add in the nitric acid and it just foams everywhere, and then slowly add nitric acid, and we want to dissolve these up in a minimum amount of water, because
don't you want to add nitric acid and just make it awful?
Again. So the less water we use, the less effort we have to put into crystallize them out. So slow additions of the nitric acid so it doesn't go too crazy. Let's get these metals dissolving.
There's a couple strips in those tags so they freak out under certain magnetic field frequencies, alerting the alarm. Oh yeah, that does make sense. They have a very high magnetic susceptibility, don't they? They're like different from regular metals in that sense, where if you expose them to a magnetic field, they can like elastically go back and forth between being magnetized. I remember I had to do a PowerPoint about this once since like my undergrad, but I can't quite remember what I had talked about then. Oh, but anyways, hey, look at that. Oxidizing the metals. Woohoo. Making salts. This one's such simple inorganic chemistry, even somebody who doesn't have an inorganic background could do this without creating tar. It's great. It was funny, the other day I was cleaning out my water pitcher because there was kind of like some yellow residue in there from just, you know, filtering out crap from the tap. And I brought out my sulfamic acid that I keep around for a different hobby that I wanted to work on at some point. And yeah, after I cleaned it, it actually worked pretty well getting rid of the stain.
Hotter, the vials will shatter. Man.
The vials are not going to shatter from the nitric acid melt, Tom. I had, you know, a sulfamic acid solution left. I tossed in some magnesium chips and just got to watch a classic, you know, magnesium reacting with acidic solution and making some hydrogen, just for funsies.
Gotta stop doing that.
Played with those, okay, so you're saying you played with those metallic glasses when you were little, suckers flex back into place. Can't crease them without breaking it too. Yeah, they're not exactly very flexible.
Solution. The ytterbium also completely dissolved and formed a nice clear solution here. The yttrium, all the metal's gone, but there's a little bit of powder at the bottom. It might be nitrate sort of precipitating out, but it might be some hydroxide as well. I should check that it's acidic and add more nitric acid, because we don't want any hydroxides. We want it all to be dissolved into the nitrate.
Wow, if you had a hydroxide in there, Tom.
It's a bit strange, so it's a bit cloudy, but these two look really good. These would be reasonably concentrated solutions, but we do want to crystallize it out without decomposing the nitrates. I've got some crystallizing dishes here, so I might put them over to this and try and drive off all the water and be left with some really
Time
nice
for Tom's favorite chemistry, the kind where you leave it alone for 2 weeks and come back later.
And this is a food dehydrator. I last used this, and the reason I got it was to dehydrate some McDonald's. Ooh, nearly dropped it all. Dehydrate some McDonald's, and there still looks like there's some McDonald's crumbs at the bottom. I really should clean that up before putting my nice solutions on there. I'm just thinking maybe this is a nice way to evaporate solutions down. It's just going to blow
He really should clean it. He's not going to.
So it's not going to overheat the solutions. Like if I just left them on a hot plate, they could boil dry, and then, you know, the crystals will start to decompose. Just trying this out. I've had this food dehydrator sitting around. Probably not safe for actual food, because I put some very old McDonald's in there and then didn't clean it. Might as well use it.
The Bacchus reaction mix got all munted.
We'll see. Hopefully it doesn't blow too many crumbs. I should have cleaned it. But anyway, let's get this cranking. Just a small amount of solution in each of the ones.
Later he'll be wondering, how did I get Bacchus in my solution?
One is kind of cleared up with a little bit more acid. It's still a little bit cloudy, which is a bit of a shame, but the ytterbium's
why is my doped yttrium oxide giving off golden arches? I don't get it.
Fine. It's fine. just always feel like
It's fine.
half
The
of my
best part of
bloody
chemistry,
time in
denial.
the lab is spent heating
The
up
best
solutions
safety
and then
concern.
cooling them down again. Like, oh, I can. This is hours. Oh, and temperature. Okay, 55 degrees. Let's go 65 to start with.
So this is the first time you've used this, right, Tom? It's not. It's not the first time you've used this. Sure doesn't seem like it.
Probably, actually. Maybe I should do this outside. 2.5 hours later, and the food dehydrator has worked its magic. Things look pretty dehydrated. I wouldn't say dry, but
you're curious if dehydrated
crystals in there.
Ooh, look at those crystals.
A little bit of liquid. So
look at that. All right. For the non-chemists in the audience, and even for the chemists in the audience, it's fun to take a look at crystals every once in a while. See if I can't get a decent YouTube still. But yeah, look at that. You can see those big needles forming there at the bottom. I love watching stuff crystallize. No matter how experienced you get with chemistry, you never quite get sick of seeing a good crystal form. You're curious if dehydrated McDonald's tastes good or bad. You know that microwave McDonald's is an absolute travesty that would make God weep. Yeah, so he tried a couple of the dehydrated McDonald's in his trying to make it flammable video. And I think the overall review is it was just kind of strange, where a lot of that kind of freeze-dried dehydrated food is just very what is it? Powdery. It just has this kind of wrong powdery texture to it, with a couple of things being kind of crunchy. And I think he was like, the flavor was fine, but it was just kind of off because of how aerated and the light texture that it kind of had. Though I think he did say that the freeze-dried pickles from the Happy Meal or whatever were like actually really good. I mean, it's pickle chips. It makes sense why that would be good. Yeah, the nitration of the meat, making nitroglycerin. Yeah, again, the best safety control is denial. Just don't think it will happen, and it won't. Simple. It's mind over matter, quite literally. Although I honestly, I will admit, there is a part of me that would love to try to purposefully make make nitroglycerin out of just trying to, nitrate some meat. I would want to, I want to fuck around. I don't really, and I kind of want to find out, but not enough to void my apartment lease. That would be a bad idea. And also American healthcare. That's not gonna, let's not work with that risk with American healthcare. It's not gonna go so good.
A little bit of liquid, so it's not fully dry yet, but done a reasonable job of removing quite a bit of the water and acid vapor, I guess. Looking good. I reckon I'll just chuck these in a desiccator now and let them dry fully before we move on to the next step. Look at that. Lovely stuff. Oh, I mean, I was hoping for much nicer crystals, but I suppose driving off the liquid while it's hot doesn't really give it a chance to grow nice crystals. The solution gets even so better concentrated because it's hot, and then it just sort of freezes as opposed to kind of slowly growing nice crystals. But that's really a problem with growing crystals of stuff like this, which is just really highly soluble. By the time it wants to grow crystals, there's just so much of it crashing out at once that it doesn't grow so nicely. But still, I'm not complaining.
I'm not sure if that's why Satan stays in hell.
Crumbs in our reaction.
I feel like that's more of a God thing to fear. Maybe he's just proud and is just waiting for his soldiers to come down.
Let's chuck these in the desiccator, and by the time we come back, should be nice and dry. The powders have been drying in the desiccator for about a week now, and they look fantastic. Look at this.
Wow, look at that. A Tom synthesis that didn't end in like tar.
Ooh,
amazing.
Nitric acid. A little bit too much acid left, but they look pretty dry. Look spectacular.
Okay, I mean, I guess the plastic cutlery worked for him. So
we also have the yttrium. Little
okay, Tom has it. It's not expensive to buy a nickel spatula. Can Tom just buy a fucking nickel spatula already? Like they're just common pieces of labware. I know that they're like. I love the fact that he's committed to the fucking shed in the back of the woods aesthetic, but like just get a nickel spatula. The plastic spoons make everything so much harder. I like watching him do that, like try to scrape it out with a plastic spoon. I'm like, that thing is going to just suddenly bend back forward and all of it's gonna go on the floor again. Like just I don't know. Hey, I'm also a safety guy in real life, so you know, that's kind of the lens I'm kind of stuck on and seeing something like that. But anyways, yeah, Crystal Crash Out has like a Sonic Zone sound to it. Yeah, it really does. It kind of does. It would be maybe at least more like a. It would definitely be the name of the theme, maybe not the name of the zone. I would say. Yeah, he has a magical way of turning organic into tar. It's amazing. My favorite is when it's like it was that Halloween video where he was trying to do the thing of making calcium from bones, and it's like the entire synthesis would have gone better if he just would have kept burning the bones and getting rid of the charcoal on it. I don't get it. I know he's not a synthesis guy, but like just burn the damn organic carbon off of it. Wouldn't that occur to you? No, it just Tom thinks that there's fucking carbon on it like that, mate. Like, just it'll be fine. Wash off the carbon, and you can get to the calcium underneath. It's like no, you burn the carbon. That's the point of the fire, and then that's why you got tar calcium at the end of it. How did you manage to get tar calcium? Oh well, whatever. Anyways, I'm crashing out right now, so I better stop whinging. So you can throw the spoons of the way. Yeah, you know. The baby turtles deserve some spoons too, especially ones colored in heavy metals. Yum.
Yellow, but still pretty nice. I'm not quite sure what color it's meant to be. The picture on Wikipedia is very white. It's not this yellow, but it's nearly green. So I'm going to.
He managed to get yellow again.
Color actually instead. Yttrium is still drying out, but is looking pretty good as well. It's hard to see, but those
crashing out's normal emotion. How about I read a
really
fucking
nice
book? Yeah, you're right.
Really
hey, D-Prototype, what's up?
I want to make just an erbium doped one, and then a ytterbium and erbium doped yttrium oxide.
We're currently watching. We're currently watching the synthesis portion of the video where he's actually doing chemistry instead of explaining heady quantum mechanics orbital concepts. But the basic idea is that we're doing this because this is a way to try to get photons of low energy light to come together and then be re-released later on as a higher energy light source or a higher energy photon of light, which is difficult to do under most circumstances unless you do some fancy kind of chemistry and engineering. And the importance of this is like it's really good in photo tagging for like biology applications, or what I'm more familiar with is getting more efficiency out of solar panels and photovoltaics. But I mostly love watching this guy for the shed chemistry. It's great.
We might as well just do the erbium doped one first. Thing is the yttrium and the erbium are dry first, and we'll let the ytterbium dry out a little bit more. And we can now get to the combustion synthesis now that we have our oxidizers here. I don't think they're very powerful oxidizers, but they're still actually, I mean, the yttrium nitrate by weight is a lot of
still use the solar power in a scam.
So
don't worry.
3 nitrate, there's quite a lot of nitrate. So this is what really drives the combustion reaction, is the fact that there's so much nitrate here. And our fuel for this one, I mean, we're following the paper, and this is a common fuel, is glycine.
Glycine?
So I went on eBay and bought some glycine. Have a look at this glycine. You ready for this?
Oh, no.
Samsung Nutrition. Look at this, man. This is how I'm trying to be this year, I guess.
Oh, no. He bought the alt medicine glycine.
See me in my fucking 8-pack later on. Quads the size of my head. 100% pure L-glycine powder. Nutrition. Gonna be using this nutrition powder to fuel our combustion reaction. Remember there was a meme about glycine, what was that, 2 years ago or something on TikTok?
Donghua Jinlong.
Does anyone remember this?
I don't remember this meme, Tom.
Why is Donghua Jinlong's industrial-grade glycine of high quality? Industrial-grade glycine produced
Oh no,
by
I kind of do
Donghua
remember this
Their
actually.
stick to strict
For
production
some reason,
standards
there's
like FCC, E640,
industrial
USP, and
Chinese
JFK.
industrial
Pesticides and
propaganda on
non-toxic
TikTok.
Industrial decarbonizers have a wide range of applications. It's your top choice for quality.
I should have tried to get some glycine from Donghua Jinlong. Was that the name of the thing? We're going with the fucking 8-pack, man, glycine instead. So we need to weigh out, it's about 3 grams, although I don't think I'll have quite enough for 2 3-gram batches, so I'll scale it down to about 2.5 grams, and only a small amount of the erbium. We're just doing it as the paper does, and which is about a 5% mole solution. I think they use a 5 mole %. So it's only about 80 or 75 milligrams of the erbium nitrate and about 2.5
you know, that's how
grams of
memes
the
are
yttrium
nowadays,
nitrate.
Grim.
And then
Only about 4%
just
of
over a
people will
gram
ever
or
actually
so
see the
of
meme, and somehow that
glycine.
means
What
it's
we're gonna do
viral.
is going to dissolve it up in a minimum amount of water. So I'll just weigh it out first, and then we'll try and dissolve it
I'm
up
actually a little
really
bit
small amount of
I mean, if I paused to have read the
This is
paper,
all
I'd
the
probably
stuff weighed
understand the
out,
chemistry a little
so
bit
we've
more.
got,
But I'm actually a little bit curious of like what chemistry he's actually trying to do here. I think he's just trying to. I mean, I know he's trying to make the metal oxides like a combined thing. I guess he's trying to only partially combust the nitrate ion. I guess, quote unquote, combust the nitrate ion to take off an NO2 and leave only oxygen behind. And he's going to use the glycine as just some organic crap to oxidize off with it. It's an interesting way that someone went about developing this. I guess that's probably the best way to make a finely divided oxide powder instead of trying to make powdered metal and then oxidize it at extreme heat and hope that it actually all fuses together and doesn't just become a heterogeneous puck or powder. So it's a fun roundabout way to get a mixed metal oxide. Fairness, how many people in chat know about the Sagwa the Chinese cat? Don't forget your umbrella meme. The name sounds familiar. I feel like my friends maybe knew Sagwa, but I didn't.
Beaker here. Yttrium nitrate.
Okay,
We'll
so
carefully pick up and not spill everywhere over this lovely clean bit of wood here that serves as my workbench, and the small bit of erbium. Okay, great, fantastic. So we want to dissolve this up in a minimum amount of hot water, and then we got to do the combustion reaction. Actually, I'm just going to pull up the paper, and I'm going to read it to you what it actually says, and let's have a think about how they might actually be doing that. Here's the paper. It's a co-authorship between a chemical engineering lab in Republic of Korea and a Department of Physics lab in India, which I thought was interesting. Come over to the experimental section. Here we go. Here's the combustion part. Metal nitrates were mixed with minimum...
I know it's a highlighter, but that is orange as all hell. The color balance is insane on this.
Quantity of deionized water in a Pyrex glass dish of 300 ml capacity to make a solution. Makes sense. The solution was introduced into a muffle furnace preheated to 450 degrees.
I fucking hate furnaces. my job is currently making me hate high temperature furnaces because I have to review everybody's attempt at using one with flammable gases in there, and it just takes so much effort to review and like tell them like actually this is a highly regulated process that you're doing, and there's so many governing bodies that have like a say in how this can be legally done, and it's just like but we don't want to spend that money, or like we think that it's fine doing it this way, we've done it for years, and it's like why did I ever volunteer to start reviewing this? Why did I open that Pandora's box? Anyways,
afterwards, the solution ignites and burns with a flame, yielding voluminous solid mass. I mean, think about that. Imagine if you owned a muffle furnace and someone was like, hey, can I put something in your muffle furnace? And you're like, sure, what is it? And they're like, it's going to ignite. Is it really a good idea to put something that's going to ignite in the muffle furnace?
Feels like the point of a furnace.
Bad for the muffle furnaces. Those muffle furnaces are expensive. Surely
that
thing
kind of
gets
furnace.
Just filled up with smoke.
This'll be
How
fine. It'll be
many
fine.
times can you run a combustion reaction in a muffle furnace before the sides are all caked with carbon?
Well, Tom, see, the thing is, if you actually do your math correctly and you make sure to add an equimolar amount of your glycine fuel, that is the minimum amount you need to actually run the reaction and mathematically have it be the mathematical minimum to actually cause full conversion, you're not going to get soot and smoke all around the sides because the burning will happen cleanly and it'll make carbon dioxide. I condescend, but this man is like very smart. I'm making jabs, not seriously hating.
Maybe it's exhausted or vented. But, you know, maybe it explains why the physics department has to work with the chemical engineering department from Korea while they're in India. Because you think, why doesn't the chemical engineering department in the Republic of Korea talk to their own physics department? But maybe they keep destroying so many muffle furnaces they have to go international to find collaborators. Anyway, we're not going to buy a muffle furnace just to ignite
Made too many enemies at your own university. Go find a different one.
Mistreating equipment, and I'm definitely not one to talk about mistreating equipment. I mean, look at my hot plate.
And your food dehydrator full of old macas.
But it's just funny reading it in papers. Maybe that's a standard way of doing it. I don't know. Instead, we're going to just put it over an open flame. And flame will be 600 or so degrees, and hopefully it ignites. We've got this 400ml beaker. We're just going to preheat it a little bit. Just get the solution really hot, just so when we put it over the flame,
put it over
it'll drive off
open
the water
flame.
quickly and ignite it. The idea is to not slowly drive off the water so everything crystallizes out. It's to really force off the water very quickly so everything mixes really well and then ignites. So you have this nice kind of nearly perfect mixing and small particle size of the oxide when it ignites really quickly. A minimum quantity of water, how much do we think? A couple mils? Surely if it's hot, it's probably all going to dissolve. So once it's hot, close to boiling, go outside, open flame, let's get this sucker burning. Let's go.
God, I'm trying to think. How is this?
All right, it really only took...
Because the thing is always, it's that when you do chemistry research, you always take the simplest path forward you possibly can. And so if your research kind of requires you to use a furnace to actually get this hot versus using an open flame, you know, I feel like there's a reason for that. And I know why, you know, obviously he's trying to do this on a more economical kind of basis and not having to buy a big piece of specialized equipment. But I feel like this is going to be bad somehow. It's not like the temperature's not that controlled. It might run away too much in the beaker. It might be too exposed to oxygen or the cold air around it. There's something, I don't know. I don't feel good about this.
1 or 2 mils of deionized water, and it all dissolved into this syrupy mass, which I've got close to boiling on the hot plate. So we'll chuck in there now.
Hey Gabriel, the grimace on the shirt is giving him too much confidence. It is a symbol of power, so
And we're all good. I'm gonna stand
he's
back.
fueled by the purple shake.
It's quite hot.
It's clouding his judgment. I also love the fact that this is like a fucking French fry basket you would use in an air fryer or something. Ooh, hey, that's cool.
We've got a little liquid in the bag.
Oh wow, look at that. It's like that that Pharaoh's serpent reaction that freshman
Just like that. Synthesis of our
teachers love to do.
third-like product is complete. Look at that. Nice voluminous powder. It
The
didn't all
incubus
ignite
is
at
rising.
once, which ooh, don't want to breathe in those metal nanoparticles. Don't think I filmed it very well, by the way. Sorry. But we've got another one to do anyway later, so it looks like it worked. And there wasn't actually that much smoke, so
I guess
maybe
I
was
stand
too quick
corrected.
to judge about doing this in a muffle furnace. It might have been fine. A little bit uneven. I suppose now we've got to calcine it. That's the next step. So maybe all this carbon just goes in the calcination step, and we're just left with the oxide. That's probably the case. Anyway, the next step is to get this, grind it all up, without trying to breathe too much of it in. Oh man, is it putting off.
Well, Tom,
ash.
if I memory recalls, you
So
do
you'd
have a
be
ball
called
mill. You
rare
could just
earths,
throw it
a
in
heavy
there.
metal. But I suppose erbium's a heavy
I doubt you're
metal.
gonna do
It's
that,
not
though.
as bad as lead, but we will grind it up outside because it looks like it's putting out a lot of weird oxide particles that will poison my body in new and unknown ways. But
He's actually not exaggerating too much there. Nanoparticles are mostly for the non-chemists in the audience who might not know, but nanoparticles are kind of a new modern concern within the safety world, lab safety world, because they haven't been studied for very long. They're kind of been, you know, maybe the hot new thing of the last 2 decades, and the health effects are unclear. And what's more about nanoparticles is that once you hit that nano size, your skin is permeable to nano-sized objects. So if something is on the nanoscale, it can, in theory, seep right into your skin and go into your bloodstream. So it's a very difficult exposure route to control. So there's some fear to have when it's just some completely unknown thing that could very easily get into your bloodstream. Yes, calcination, dubbed from back in the alchemy days. Fucking good old alchemy, mate. That's where chemistry really began, you know? Just doesn't want to. He just refuses to say the word annealing for some reason.
I'm interested to see if this stuff is going to light up under the laser already, because our next step is the anneal step, and I think the anneal step is really important to...
Yeah, I doubt it's going to line up under the
carbon,
laser.
But also improve the crystal structure of the oxide particles, which
primarily
will,
for that reason.
Improve their luminescence behavior. So I'm interested to...
If the crystal structure doesn't... Because the annealing will form the crystal structure for this, and the crystal structure is very important for forming the orbital shape that allows for the absorption and release of visible light. So without that annealing step, you might get a very, very weak luminescence out of the atoms that have just so happened to bond in the right way, but I think without the annealing to kind of get everything to move into place, it's not going to work very well.
Pre-annealing, this stuff lights up under the laser. So to do that, we've got to get our laser out. It's a bit intimidating. I've handled lasers many, many times before. A lot of them more intense than this, but never in this rat shit shed before. It's a different vibe. Here is our laser. I've borrowed some things just to make this actually safe enough to do this bad boy here. Now, it is important to start this discussion with mentioning that this cost me $75 US, which honestly is amazing. So when I start talking shit about this laser in a second, I have to remember that I did pay only 75 USD for this. Put them in this post here. And I'm facing downwards. All right, fantastic. So this little guy is a solid state laser. I measured the spectrum and the power coming out of it. It is just short of 980 nanometers at like 975 and only produces about 400 milliwatts. It says on spec it's about 500 milliwatts. That's fine, really, honestly. Half the time these kind of Chinese import lasers are over-spec'd, well, like much more powerful than they are spec'd to be, which is quite dangerous, but 400 milliwatts is fine.
There's you don't want a laser that'll instantly blind you.
This is a tiny little dial, and I was interested to see this was going to change the power output, and it does, although I'm not entirely convinced that's intentional. On the eBay listing, it just says that this is a TTL delay, which is about pulse lasers, and it may be because of this third input here. There's a space for a third input, which may be a trigger to try.
I know very little about lasers.
Pulse, and when there's no input, it just runs at CW, which is what we want.
I know my basics how they operate, but I don't know how the actual mechanics work. Once you get to physics, you lose me.
12 volts from the wall. There's no on switch, which I don't really like. Also, there's really no labeling on the laser, which is not great for an IR laser. You can't even tell really when it's on. It does have a little focusing lens at the front. I didn't really play around with that too much.
It's a safety hazard for sure.
It does terrible things to the beam quality. I mean, the beam quality and the beam profile out of this thing might be terrible. Once again, $75 US. Just because I'm used to university laser budgets doesn't mean I'm, yeah.
Neither are electrons, Ryan.
Insult the 75 USD laser. We just have a tiny bit of our material here. I really don't have a lot of confidence that it will work before annealing, so we might as well keep the rest of it for annealing. But let's turn this laser on.
It's not like you can't just re-add it back.
I'm interested to see if the phone will pick it up.
Shooting the laser's not going to ruin it.
Be able to pick up this 980 nanometer light, especially with the glasses on. But sometimes the phone can pick up infrared laser wavelengths. Depends on what the filters they use. Got my glasses on, so I can turn him on.
Where do the tachyons come in?
I can see that
literally
through the glasses.
Literally in a advanced physics lab, looking for sparse particles of the universe that barely come out of most interactions with matter. But I appreciate the Death Grips reference. That was me learning oxygen's ground state was a biradical. Yeah, true. It really does kind of make chemistry feel fake at that point. The fact that those two just don't want to bond because it's like, well, actually, we have our own orbitals on each, well, not literally, but, you know, on each oxygen. So, like, we're cool out here. And it's just like, oh, no, you're making oxygen have only 7 electrons each. Why would you do this? You weren't even trying to make one? Oh, well, that's what I figure most people are trying to make one when they say tachyon. Oops. Awkward.
On the IR viewer card, thanks Thor Labs. spent a lot of money at Thor Labs. And then the camera can't see shit. The camera can see kind of what my eyes can see. The older phones, I mean, like phones from a couple of years ago,
Would have been
the previous
Yu-Gi-Oh
iPhones
reference.
could see this IR beam. But
Not as familiar with Yu-Gi-Oh, but that would not surprise me.
Extra IR filters. Whoop.
Or at least the Photon Dragons part.
Things on fire. Yeah, you can
Setting it on
if
fire?
It starts to set things on fire. You can see it burning through the black there. Sorry, card.
Shh.
Yeah.
Congratulations, Tom. You have a
400
powerful
milliwatts is enough
laser.
to start fires, I suppose. Well, I mean, it's black card.
Tom, you should. Oh my God, he should use the laser to try to heat up some Makas on his next video. Can I use my 400 milliwatt laser to heat up McDonald's?
It's gonna melt a little bit. Burnt plastic smell. Right, glasses on. Turn my laser on. I don't think you can see it on this camera either. Nope. All right. Well, invisible beam. All right. So the question becomes: can we make our invisible beam visible by using our upconversion material? So this is obviously pre-annealed, and this is
Come
just
on,
the
Tom,
erbium-doped
stop
one.
teasing us. I want to see it.
Yttrium and erbium doped one because our ytterbium nitrate is still drying off, so we have to make that one still. But for now, this is all we have. Erbium emits in both the green and the red under these conditions, so you get sort of a bunch of green spectral lines and a bunch of red spectral lines. And changing the co-doping kind of changes that ratio of red to green. According to the paper, their just erbium one had more green than red, and their co-doped one with the ytterbium had more red. So this is just the erbium doped one. So we're expecting to try and see some green light come off this sample.
If you edge your crystals, they'll have bigger luminescence at the end. This is a true fact checked by real American chemists.
Looks like it's hitting the sample. Can't really see any green there.
Well, Tom, it does help you have the entirety of the bright sunlight on it.
Sad. This is what I fully expected. Probably only works after the anneal step.
Tom, I think there was a little bit of a notable color shift, but like you have the full force of the Australian sun behind you. If you could maybe close the shed, you might have been able to see the weak luminescence coming off of this unannealed sample.
So let's get to heating. Let's go find a goddamn furnace and start heating this shit up. All right, we need to heat our formed oxide at 800 degrees for 2 hours. Now, 800 degrees Celsius is too hot for a hot plate, which probably gets to about 350, and too hot for a gas stove, which probably gets around 600, 650. So I have bought a furnace, which is in this box, and we'll see.
Pay money for this
because I ordered this a long time ago. Chinese manual? Hell yeah! All right. I don't know. I don't know if this is really the right thing for us. Actually, I'll correct myself. I know this is definitely the wrong thing for this task, but it was surprisingly cheap for this.
Of course, it was a bargain. That's why you bought it.
Once again, a bit of a red flag.
Tom thinks exactly like a fucking principal investigator of a research lab. Is it cheap? Okay, buy it then. That's not what the right equipment for this job. Just figure it out. Just do some ghetto engineering. Like that's what you have a chemistry degree for. Do ghetto engineering and like you'll figure it out.
But it's a lot cheaper to get to these high temperatures using this for a sustained period of time than using like something more like a muffle furnace, which are quite expensive. Ideally, if we just needed to get it up to 800 degrees and go back down again, I could do something like I've done previously and do the microwave furnace, which does get us to that reasonably high temperature quite easily.
That's the devil's shop, Ryan. So clearly the devil does actually not hide from what he, the fear of what we created.
Sustain things for a long period of time.
He just sells you,
It may overheat if we have it for
just cheaply manufactured electronics that may or may not actually do their advertised function.
Please read these instructions carefully. Right, and there it is, all the way from the People's Republic of Italy. Okay, Italy. Maybe Italy is the brand name. Yeah, look at this bad boy.
People's Republic of Italy.
Graphite crucible, correct power cord, which is always nice. Tongs. All right, this is feeling
our
like an
antipasto.
Let's get on with it.
There you go. To ensure a long serviceability, to ensure a long durability and good function.
Rare cameo from his dad.
Strongly advised to work less than 3 hours at once.
Okay, 3 hours is okay.
Please ensure you stop for 30 minutes after 2 hours of continual work. That's right. Don't breathe in too much lead.
Nah. All right, the furnace does indeed get hot. So it's time to heat up our material. We've got our material here. I'm on the floor just in case everything catches on fire, then it doesn't melt my precious plastic table.
I don't think it's going to go that bad,
ground
Tom,
up
but
powder, brown powder
plus one
into,
for safety,
this
so.
crucible here, which needs a bit of wash. It's got a bit of graphite on the outside, and we really don't want to introduce that into our material. Ideally, we'll be using, you know, some ceramic holder or something, but I'm just going to use the graphite, and hopefully the graphite doesn't interfere too much. I think we're all good to go. 800 degrees for 2 hours. Trying not to break this thing by letting...
Using the graphite's a bit of a gamble. That at those temperatures, that is a fuel that could react with your oxide, so
it overheat.
Good luck.
Much. But apart from that, we've got a bit to do. This is just the erbium dope sample, yttrium oxide doped with erbium, but we also have our co-dope sample still to make. Oh, you can see it glowing in there. Fair enough too.
It's alright, Tom. You'll be fine. Nile Red bought this same kind of thing years ago, and he didn't cause anything bad. He just made purple gold with it.
Initial nanoparticles and anneal them too. So quite a bit of work to do. I feel a montage coming on because I'm going to go blast the cricket on the radio and listen to Australia play cricket. So.
Alright, good. He actually remembered to close it. It would have been so funny if it's like, I can't get it to heat high enough because I didn't close... I don't know why. Lid is still open. No insulation. Hey, that's nice and cleaned up looking. That's just a lovely white powder. Can't believe it. Tom might have actually had a completely successful synthesis. Tom usually makes disasters the first time. It takes him a couple times to actually get somewhere good. And it rises. There we go. More demons. Hooray! It's fine, Tom. Lose like 10% of your yield to the fucking wind because you can't be bothered to pour well. Oh my god, he's losing so much! He's losing so much to the wind, dude. Just like, just don't pour it in the wind.
Fantastic.
True, it does look like some good dark chocolate.
Laser again with two different
full of nanoparticles. Yum.
Look at this, fantastic. This is just our erbium sample and our co-dope sample. So we have our laser, we have our powders. Let's see if it all comes together. I'm a little nervous. We're putting in a lot of effort here. Let's do it. Got my glasses on. Let's crank this thing on. Nothing.
Tom, it's bright as shit outside.
What about the co-dope sample? No.
Tom, it's bright outside. Tom, you need to go in the dark.
Maybe we'll go somewhere dark. Maybe
there we go.
Very, very weak.
All researchers do this kind of thing. It's like we have a dark room.
Let's go
We're
somewhere
gonna have
dark.
outside light interference.
Then we can get sad. I don't like using lasers in the dark, but let's go.
Oh, and his frame rate dropped. You can tell he's using the something much lower. Oh, look at
You
that.
can see it. Right, but it is there. I mean, under the glasses it's kind of like a white light, but I assume it might be a bit red. Now for just the erbium doped one.
It should be more green. And there it is. You can see that little green dot. See? It did work.
Again.
It's just that, you know.
It just can't really compete with the full Australian sun. It is a lot dimmer than the IR card, which will give people in optics a bit of a reference for kind of how bright it is. But we've done it. It's totally there. What colour is this one? I honestly cannot tell through the glasses. The
imagine it may
be
be
brighter than the just erbium dope sample. It's got more dopant, but
I imagine with maybe a you know, a cleaner, more professional lab setup, you could probably get a little bit better of a emission out of it. But it's still pretty cool that they, you know, someone managed to create this you know, stuff useful for photovoltaics and other applications. Something that in organic
really,
would be difficult to
that's
do.
absorbing the infrared light, which is really driving this this higher brightness. You can see it's totally photostable as long as the laser doesn't set fire to it. But
now I just need to ask, where's the photons? Can you click on the photons?
Rare earth fluorescence, but it's turning that infrared light into visible light out. Isn't that cool? I really panicked that this wasn't going to work at all just before. But it is. It's totally working. Okay, so yes, maybe it is too dark and too dim to see in a brightly lit room, or like a normally lit room. This is kind of what we expect from the paper anyway. I mean, the thing that's lacking from the vast majority of upconversion papers is a scale of, I guess, its absolute brightness. I mean, if we look at this plot here, we get these nice peaks in the green at 550 and you know, in the red around 600. First of all, they're putting in 2 watts, 4.5 watts of laser power, and there's no sort of absolute scale. This is just arbitrary units, and it really depends on how sensitive your spectrometer is. Who knows, maybe they focus this laser down as well. There's no sense of the power density. 4.5 watts could be 4.5 watts spread over a big beam, or a tiny
it's easy to publish when you don't have to
the focal point of the spectrometer.
Talk about really like the actual practicality, the objective
while
number.
They do work and the graph looks nice, in reality, you know. Anyway, I'm still extremely pleased with this result. We got to combust some stuff for a reason. We got to use a metal furnace and it didn't blow up. We got this laser and I didn't get blinded. I've had a lot of fun. So, if you've enjoyed this, I mean, fucking subscribe. I never tell people to subscribe. That feels cringe. Consider subscribing.
Yeah, you and me both, Tom.
It's fine.
You and me both. But yeah, no, although I would say probably, you know, to be a little bit fairer to the paper publishers, it is kind of like, when you're working with the photovoltaic, I mean, yes, it is like kind of getting the full intensity of the sun, but like you're mostly just trying to get it to, you know, produce some extra visible / UV light on top of what and have the other components of that photovoltaic absorb it rather than this be like the primary thing. So like, you know, especially it's also you would have this like usually like right next to said photovoltaic component that would absorb the visible light or UV light. It doesn't need to be that absolutely strong. It just needs to be able to, you know, have some transmission of higher energy light over a short distance. So yeah, no, that was interesting, and that's probably the cleanest product I've ever seen Tom actually produce on his channel, at least in a very, very long time. So yeah, no, I don't know, that was cool. Any questions, class? Any other fun chemistry things anyone wants to ask? Otherwise, I'm thinking of probably calling it a little bit of an early night. I know I normally do 2 hours, but I scheduled a thing with a friend, and well, then I remembered then I said I'm going to stream on Thursday, and then I remembered, oh shit, I said I'm going to stream on Thursday, oops. So, yeah, maybe I ought to go get to that. But, yeah, no, I love Tom's publications. It's always fun to see what he can manage to do in a, backwoods Australian shed. And, he always has a very good balance of, humor and, actual science on display. He's a great dude. I would encourage you to go just subscribe to Extractions Ire and Explosions&Fire if you are not already. Because he makes some quality shit. And if you don't care about the science as much, the Explosions&Fire channel makes a hell of a lot of explosions and fire as expected. And hey, that's entertaining no matter who you are. But anyways, yeah, thank you for joining me tonight on my, oh, wow, even appropriate. We're getting, oh no, this is the shop theme. Never mind. Thought this was the credits theme for a moment. Yeah, thanks for joining me and checking on in with me and my science shtick. You know, if you like, hit the like, subscribe, hit the subscribe, blah, blah, blah. It's cringe, just like Tom said. It's hard for me to say, but, you know, appreciate you all being here. If you want to stick around for more, you know, there certainly will be more. I don't know when the next chemistry reaction video will be. Kind of depends on when, you know, Nile Red or the CSB decides to put out another new video, or maybe another big chemistry channel will come along and be like, ooh, I have to talk about this. You know, next week we'll be doing, resuming Mega Man X8 on Monday, enjoying that game, eager to get back to it. And then on Tuesday we'll be resuming Doom 2, you know, towards the last handful of levels. I think we're on, like, what, map 24? No, that's probably too far. I forget what map we're on, but we're, you know, towards the latter third of the game, 23. So we're doing that on Tuesday, and oh yeah, special extra thing. So I do actually want to say that, like, so that, remember when I was talking last year, maybe some of you do, when I was talking last year about how me and some of my friends do a special worst of that year's songs podcast every year. Well, I haven't forgot about that. I know it's mid-February, but this is actually maybe the fastest turnaround we're having on that video. It's almost done being edited. You know, that should be done probably within a month. But in the meantime, we will be re-uploading some of the previous year's videos with a couple of edits, mostly to scrub out some personal information that I don't want on the internet anymore. So once that is, and we'll be releasing those kind of in every week until the 2024 one is ready. So hopefully by the end of this weekend, there will be the 2021 podcast, or record, when I say whatever, I guess it's a podcast, the podcast uploaded to YouTube. And I will advertise that once it is actually released. And so you can have not 2 hours, I think maybe an hour and a half of Crash Icarus yapping with his two friends content for, you know, a while. Hopefully it's not copyright hell. I mean, I think there's a little bit of copyright stuff, but this is also my friend's channel who, like, she doesn't particularly care about ever, like, making good money or being, you know, she's not exactly large either, so she doesn't have to worry about, like, getting, you know, copyright striked and banned off YouTube so much. Usually nowadays, for small snippets of audio, they'll kind of YouTube will just kind of, like, you know, slap you a little bit and be like, oops, sorry, we were going to take the ad revenue for the company now, bye, rather than straight out ban you. So, you know, that one will work out. It won't be on this channel, thankfully. I don't think I would maybe do that, but it'll be on another channel, so you can go watch that there. Get an hour and a half or so of yapping content, and then, oh boy, that warning is kind of ominous on the music, huh? Well, we're just gonna power through. And, you know, you'll have some fun stuff to talk about. And, eventually the 2024 one will be uploaded. So, I'll let everyone know how that goes. But for now, that's gonna be me. That's gonna be it for tonight. I'm signing off. Thank you for joining me once again. That's like the 5th time I've said that. Good night. Eat those vegetables, and don't make tar, kids. Tar is the enemy. Good night.